然后先请两组先自我介绍一下 ，A 队先请。对，组介绍一下，就是自我介绍一下。
这是有人上面。
都会看。
The name of our team is IonSuperMn, and we are from National Experimental High School, and our topic is Pendulum-Radial Azimuthal. So, so we have done some experiments, and so it is our presentation.
Hello everyone, we're from彰化High School, and our my teammate is 蔡女and
Okay, so then we start the competition, and now it's 10 minutes for Team A to report their topic.
Our topic is Azimuthal-Radial Pendulum. Next page. This is our outline. First, we have a little introduce to our intro, aka the phenomenon, and our observations, and our theory, and the experiments we've done, and our conclusion. So the intro. So this is the description on the website. So this is the phenomenon we have to investigate. So the intro. Fix one end of a horizontal elastic rod to a rigid stem, and support the other end of the rod with a taut string to avoid vertical deflection, and suspend the bolt from it on another string. And in the resulting pendulum, the radial direction, the oscillation of radial direction can spontaneously convert into azimuthal direction, and vice versa. So if we start the initial state is azimuthal oscillation, the oscillation will convert into radial oscillation. So this is our observation. So we had little experiments set up to observe the phenomenon, and we have found that if the initial state is, if we start from azimuthal oscillation, the direction of oscillation rotates periodically. Periodically means that it will rotate and it will rotate back within a range of about 300 degrees. That is, if we start like at this direction, and it will start to rotate, the direction of oscillation will rotate and about to this angle, and it'll stop, and it'll go back and to the other direction, and it's quite symmetric. And if the initial state is radial oscillation, the initial direction of oscillation is radial. It will rotate too, but the angle is much smaller. It's approximately 60 degrees. And this is like, So this is our theory. So this is like with the point we analyze the phenomenon with some physics theory. So we have tension T1 on the top string, or the red string on the screen, and the force from the rod, because it's elastic, and the tension T2 on the suspending string. So these three forces together will make the green part of the rod kind of not balanced, but make it move. And if the bob like goes to a higher place, the tension T2 will decrease, and hence the sum of three forces will the direction will change, and hence the green part will have a influence on the green part, and so the direction of the pendulum will change. So, and this is our contraption of experiment. And this is we graphed this is the x direction of the bob over time, and we can see that there's two sine or cosine waves multiplied together, and the smaller one is basically the period of oscillation, and the bigger one, or the wider sine wave, is the period of the rotation. So we calculated the theoretical period from this formula, and as you can see, the results are quite close. And this is the rod, the vibration of the rod over time. And as you can see, there is a little slope there, and it is because that the camera has moved slightly, so hence the error. Oh, and different material. So we have used rod made of copper, and the rest stays the same. So we have found that copper rod, the period is much longer, and the iron rod is even much longer. And a different angle. So the initial angle, we have theta. Theta is the bob or the string, the suspending string. The angle between the suspending string and the vertical line, and phi or phi is the direction of oscillation, and the rod, the angle between them. So this is another graph. So this is another experiment in which the initial phi is 60 degrees. Oh, and 90 degrees, and that is the initial state is radial. So the oscillation, the rotation is more slight and hard to observe. So this is our conclusion. The period of rotation of oscillation increases as there's elasticity, that is, how easily the rod can be bended. The elasticity of the rod decreases, and the fluctuating tension on the taut string from the stand, the iron or metal stand to the rod, the string, its tension fluctuates over time, and that causes the change of direction of oscillation of the pendulum. So, yeah, 结束了。Thank you. Gracias.
Okay, next part is for Team B to record the.
Today our title is Radial Pendulum, and I'm the reporter. The problem is when taking pictures of a global internet, a number of waves emanating from the center of the lantern may appear in the pictures. We can investigate this phenomenon. Okay, we have to give a definition of emitting rays. Because the rays emanating from the center of the lantern, we think it's what you can see in the circle. We think it's this. And I'll talk about the theory first, and then I'll talk about the experiment and our setup, parameter data, and in the end I'll give a conclusion. Okay, the first theory is we find that it's about the aperture. We find that when we zoom the aperture, because of aperture is made of some glass, and when it zoomed, the shape of it will change. It's a circle first, but when it will become a polygon. And another theory is that we find that when the light travels through the different shape of a hole, the diffraction shape will be different, and that's when the light travels through a triangle hole. The different shape it will look like this, and it's square and circle. Okay, let's talk about our experiment. That's our setup. We have a camera and a flashlight, and the light of the flashlight is white, that's yellow, and we take a picture at the flashlight, which is turned on, and we change the shutter speed and aperture and use the different lens, and our parameter have the shutter speed and aperture, and the lens with different number of the aperture glass, and as you can see on the comment. Okay, that's our first experiment data. It's about the shutter speed and aperture, how it influences the picture it takes. We can see when the shutter speed becomes slower, it will be more bright. And the aperture, we can see that when the aperture becomes smaller, the emitting rays will become more clearly. Okay. And when we draw a cross when we can't see the emitting rays in the picture, and we draw a circle when we can see the emitting rays, and we find that when the F number is over 11, we can see the emitting rays, but the shutter speed didn't influence it. So that means when the aperture becomes smaller, the emission rays will be more clear. Okay, let's talk about the different number of the aperture slits and how it will influence it. We can find that when the aperture number of aperture blade is when it is 6, the number of emission rays have 6, and when it is 7, we can see 14 emission rays, and let's add 9 and 10, and we can find that if it's the number of aperture blade is even number, the number of the emission rays will be same with it, and if the number of aperture blade is odd number, the number of emission rays will be 2 times of it. And I give it the conclusion that is when the shorter slit didn't influence the emission rays appearance or not, but if the shorter is lower, it will be more brightly, and when the aperture becomes smaller, the emission rays will be more clearly, and the number of aperture blades is if the number of rays will be 2 times of the number of aperture blade. Well, the number of aperture blade is odd number, and the number of rays will be the same with the number of aperture if the aperture blade is even number. Okay, thank you for listening.
Okay, 2 minutes for the short questions preparation. Okay, time's up. 2 minutes for Team B to ask Team A some short questions. B 的先问 A。
Can you show me the force diagram?
What?
The force diagram.
Force diagram. Por supuesto. Force diagram. 第4个。This one.
Now I'm asking the force diagram.
What?
Force diagram.
Oh, force. Oh, fuerza.
What's T2?
T2, the tension of a suspending string. The tension, tensión.
What's F?
F, the force from the backwards of the rod. Because we separated to convenience of analysis, we separated the very front part of the rod from the rest of the parts of the rod. So the force is
How much force is there?
How much force?
Are there?
I don't know. It is a bit.
How many forces?
How many forces? 3.
3.
Of course, the gravitational force and W. So I guess there's 4 forces.
Okay, time's up. Time for Team A to ask Team B some short questions.
Do you use your eyes to judge the result or not? Yes or no?
Yes.
Use your eyes. And how do you define if there is a if there's a light, how do you define if there is or there is not?
Use our eyes to check it.
And how do you make sure that the frequency of the light is a constant, is unified or uniform? Because if you use like for example this, light consists of many frequencies, and that will affect the diffraction.
I think it didn't influence it.
But like different frequencies can be.
I think it doesn't matter.
Okay, it doesn't matter. Do you notice that the brightness of the flashlight might vary?
Can you speak careful?
The brightness of the flashlight might vary.
I can't show it, but we think it's almost the same.
And what kind of camera do you use?
What kind of camera? Digital camera. Digital camera.
Digital camera.
Yeah.
So in your experiments, you use digital camera, and the frequency of light is a very important factor of diffraction, but you didn't use the uniform frequency of light. So I think this may influence things.
Ready for the discussion? 2 minutes. Time's up. Time is for team A to ask team B. 4 minutes.
Okay, so the questions. How? No. Okay. How do you define if you see the rays or not? So you have answered.
Oh, as I said, we use eyes to check it.
Okay. And how do you set up the device to keep the light from the environment penetrating it? It might affect the result of the experiment. Like very seriously.
Sorry, can you speak in another word?
How do you set up the device to keep the light from the environment from going into your experiment device?
We put it on the table, the flashlight on the table. You say other light.
Like there's like many lights outside of your.
We do it in a dark room.
In a dark room. So how to make sure that the light consists single frequency, because frequency is a major factor of diffraction.
We just want to know the shape, so I think we don't need to know the frequency.
Okay. And the reflection from table also might influence the results. Have you noticed the reflection from table?
Reflection from table. I think it won't have a very big influence.
And you tell theory with only phenomena without explanation. Is that right? And the theory. So in your PowerPoint, in your presentation, there's no physics theory inside it. Only phenomena.
You said this?
I mean, do you utilize any physics, any theory of physics?
We use computer to make it.
use computer to analyze it or use computer to simulate it?
We use Mathematica to calculate how the light travel through the different shape of the hole.
But what exactly is the theory lies behind this phenomenon? Diffraction. So like the formula. Where's the formula? Formula. Plural formula. Okay. And would you explain the relation between your experiment and this formula, delta y equals r lambda over b?
This we find it on the internet.
Internet.
Yes, I'll make it.
Okay, let's start. Time for team B to ask team A.
I want to know, please show me the first diagram again.
First diagram.
Did you I want to know whether the first force will influence the trajectory of the regulating of the Azimuthal-Radial Pendulum and radial acceleration.
Okay. By the first force, you mean the first T1, right? T1. So while the pendulum oscillates upward, the tension T2 will change. We agree that, right? So the T2, while T2 changes, we can assume that T1 and force and F stays the same for a little bit of time. Hence, the sum of the three forces, or plus the gravitational force, which is pretty much constant, will change, and that will influence the rotation of the direction of the pendulum.
I think that your Ross coefficient of elasticity will influence the result.
Yes, it does. So we utilize different materials such as wood. First, we have wood for our experiments, and copper and iron rods. So they have different coefficient of elasticity, but the exactly amount we haven't investigated because we think it's a more complicated model to consider.
How many times the experiment you do?
How many times?
Yes, the same experiment.
Same experiment, like with the iron rod or all of them?
No, with
the iron rod.
Yeah.
We have theta equals 30 degrees and phi from.
No, I said that when the parameter is the same.
This is the same.
Yeah.
We have like 4 times.
4 times. So what's your standard deviation?
Oh, we haven't calculated that.
So okay. So how's your how's the coefficient of elasticity? And the coefficient of elasticity.
El coeficiente de ¿qué?
The coefficient of elasticity.
Oh, coefficient.
Yeah.
No, we haven't considered the. We know that the coefficient of iron, copper, and wood is different, but we haven't considered that as a factor, as a numeral factor of the experiment.
Okay, time's up. Preparation of discussion for English. Time's up. Time for the team B to manage intro. 2 minutes.
Then we think the team A they didn't cover standard deviation, so maybe there's some error of their experiment, and they don't know the coefficient of elasticity, so they don't know how it influences the experiment data. Okay, the result of experiment, and I think the first diagram is not very complete, and they forgot to write the page number, so it's hard to discuss. Okay, that's all.
First of all, we like to talk a little bit about our experiment. First of all, we haven't considered or calculated with the coefficient of Young's model or coefficient of elasticity. So that is a big factor, and we haven't considered it. So we think in the future we might consider it as a part of a model. And about their experiment, we think that the photos are very clear and it's pretty easy to see the results, and we think that they might want to use the uniform frequency of light source, and that's all. Y pensamos que sus experiencias nuestras experiencias pueden mejorar porque los factores no son actuados. So we think that both of us can be better. Thank you.
Time for Henry to ask questions. 5 minutes.
我想请教一下 A 队，那个是什么力量让它从平行变转动？
用中文吗？哦，好，中文。就是你看那个摆嘛，它摆上去的时候，上面张力会改变，绳上张力会改变。
一开始起始条件的时候 ，T1、F 跟 T2 应该都在同一个平面。
在同一个平面，对。可是然后还有加上重力嘛，所以这4个力，然后其中 T2是随时间一直在变的，然后当然 T1跟 F 也是，只是说当 T2 改变的时候，我们可以假设 T2跟 F 暂时是维持原来的状态，然后它一改变的时候，它们的合力就会指向不同的方向，然后就会改变绿色的那部分的移动，然后这就会影响到下面的白的方向。
这些合力都是指向你讲的绿色的吗？
所以我就考虑棒子前端的某一小段 他所受到的力。
那它怎么造成力矩可以转动？
让它转动。你说你的转动是指棒子的转动，还是说
那个提下摆锤的转动？
就是比如说一开始假设是这样子，这个方向的话，那
一开始你是应该是平行这根弹力棒。
那是平行的弹力棒嘛？对，那假设就是一开始如果有一些扰动的话，那它的合力就是它摆上去，它的张力变小嘛，变小，然后它们4个的合力或者3个，就先假设不考虑重力的话，要考虑重力啊，对，就是它们4个合力就会改变方向嘛，然后那个前面的那小部分，它就开始往其他比较奇怪的方向转动，不是转动，就是移动。然后因为它现在绑着摆锤，所以它会有这个方向的力矩，让它变成说原本是这样子摆，然后变成这样子摆。
那请问一下，它会不会再摆回来？
不会再摆回来。就用这个图形，用这个模型继续解释吗？
你的实验
会继续摆回来。可是就是它一开始假设是这样的话，它会这样摆，会变这样摆，然后再回来这个方向，然后周而复始的。
它有周期性吗？
有。
你们知道周期？
周期差不多是7点多。就有2个周期，一个是单摆本身的周期，然后另外一个周期是旋转的周期。
谢谢。不好意思，我想请教一下第一对哈，就是说你们在看那个几条的时候，眼睛看得见吗？
可以。
那你们没有把眼睛的条数加上去吗？
什么？
你们的 data 里面有没有把
眼睛的话是要那个眼睛眯起来看才可以看到，眼毛会让。就是你眼睛如果看灯的话，也会有类似的现象，但是眼睛眯起来看的时候，才会看到现象。正常时候不会看到。
为什么？
为什么？眼睛这部分我就不知道了。
可是你拿相机去拍的时候，你的镜头基本上跟你眼睛打开的时候应该是一样。那为什么镜头可以拍得到，眼睛拍不到？
镜头拍得到，眼睛看不到。这个部分我就不是很清楚了。好，谢谢。
还有老师要问问题，那就请老师。
我问个问题，我想请问 A 队哈，你们说那个偏转可以到300度，你们300度是定义哪个区块？
就是比如说，就是
可以用黑板，上面有黑板。
就是比如说，它原本是这样，原本这样摆，然后它这样转，这样转，然后转到这个方向之后，然后又回来，然后有点像复摆，可是复摆是，就它是一个圆周，可是它会摆回来，摆到这边，然后我们说这个角度是300度，大概啊，就是假如原本是这样，原本是这样。然后我会画，然后它会摆成这样嘛，然后再回来，然后到这个方向停住了，然后又摆回来，所以从这边到这边，又到这边，这个角度是300度。
我也可以。
用黑板，就假如原本是这样，这是俯视图，然后它会这样摆过来，到这个角度它停住了，不是停住了，就是它会反转，这个角度，然后它又慢慢摆回来，
对，
然后到这个角度它又反转，然后。我说就这个大概是300度。
好，那 一般来讲，我们在看角度会指的是它偏转的现象，所以我们应该很少会定义这个大角嘛。我们定义的是它来回偏转反折这个角会比较。
因为它是真的就是从这里到这里。你说这个角吗？
对啊，一般我们应该会定义这个角嘛。
哦，好吧，那就除以2，150。
OK， 了解，好。
还是150。哦，然后有一些影片的。
他们那边准备那个，B 队，我想简单问一下说，那你有没有想过，像你现在这个图是正6边形嘛造成的，那你有没有想过？
这是三角形。
三角形。
对。
所以那框白色的框是指什么？
什么东西？
我们现在看到的不是一个6边吗？
对，就是用那个就是在网络上面找到有那个人是用那个 Mathematica， 然后去做那个就是点光源就叠加出来的结果，它就长这样。
嗯。
对，然后是三角形。
哦。好，我懂意思。OK， 哦，后面。没事 ，OK。我懂他意思了 ，OK。
那就请老师们评分哦。那先评 A 队。8分和9分，那 B 队18分和8分。好，我们谢谢2队同学还有评审老师。